Now, the type 2 integrals are integrals that result when you're actually trying to evaluate an integral and one of the endpoints is where the function is undefined. So these include functions that are undefined at either one of the endpoints of the domain of the integral, or they might be undefined at some point in between. So for instance, let's assume that a function is not defined at b. Let's say we're integrating a function from a to b, but this function is not defined at b. Well, then in that case, we write the function. What we do is we say, okay, we're going to integrate from a to c, and then we're going to take the limit of that as the value c approaches b from the left. Okay, and that way we're approaching from between the interval a to c. We're approaching from within the interval a to c. Now, if the left endpoint is the one that's undefined, then we rewrite our integral as from c to b, and we take the limit of the integral as c approaches a from the right. Again, we're approaching c from within the interval from c to b. And then if it's undefined at a point inside, like at some point c, in between a and b, then what we do is we have to write two integrals from a to c and then from c to b, and we have to evaluate those in like fashion as what I did up here. So for instance, this function would be undefined at c, and this function would also be undefined at c because it's the same function. Okay, so let me show you an example of, let's see, this is actually an example. See, this function here is undefined at 0. So it's actually undefined at the left endpoint. So I would be doing number 2 here. Okay, because we would be undefined here at a. So we're undefined at 0 because 1 over 0 is 0. So actually what I would do here, I would rewrite this integral as an integral from c to 1, and then I would take the limit of that as c approaches 0, this number here, as c approaches 0 from the right. Okay, now you can easily integrate this using the power rule. So if you integrate, that's going to be x to the negative 2/3, and so if you integrate that, I'm sorry, negative 1/3, and if you integrate that, you'll get x to the 2/3 times 3/2. Okay, and now remember, we're integrating this from c to 1. So if you integrate it at 1, you're just going to get 3/2 times 1 to the 2/3, so you're just going to get 3/2. And I probably should have just wrote 3/2 right there. But anyway, you're going to get 3/2. Now, and then minus the same function evaluated at c. So that's going to be minus 3/2 times c to the 2/3. Okay, but we're going to let c approach 0. Well, if c approaches 0, this is just going to be 3/2 times 0. So we're going to get 3/2 times 1 minus 3/2 times 0. So we're going to get 3/2 minus 0, which is 3/2. And so this integral converges to 3/2. Okay, I'm not going to show you one exactly like number 1, but I'm going to show you one that has that actually within it. I'm going to show you one like number 3 next. So go down here and let's take a look at this one. Okay, so this one we're integrating from 1 to 2. Okay, I'm sorry. I lied to you. I didn't realize I had this one. So this one I'm integrating from 1 to 2. And so it's 1 over x minus 2 quantity squared dx. So I am going to show you one like case 1 here. Okay, so this function is undefined at the upper limit or the right-hand limit. So I would rewrite this. This goes from 1 to 2, so I would write this as 1 to c, and then I would take the limit of that function as c approaches 2 from the left. Well, if you integrate x minus 2 to the negative 2, you actually get minus 1 over x minus 2. And now if we evaluate this at c, we get minus 1 over c minus 2, and if we evaluate it at 1, we get minus 1 over 1 minus 2. So we get minus 1 over minus 1, which is 1. And then we subtract it, so we're going to get minus 1 for this term. But if we let c approach 2, we actually get minus 1 over 0 here, which is an undefined value. So therefore, my integral here would diverge. In other words, it would not converge to a real number. Okay, now take a look at this one here. I'm integrating this from 0 to 2. Okay, now you can easily see if you set 2x minus 1 equal to 0, you can see that if x is 1/2, the denominator of this would be 0. So here we know that this function is undefined at 1/2. So what I'm going to do is I'm going to actually break it up at a half, and I'm going to go from 0 here to 1/2, and then I'm going to go from 1/2 to the upper limit 2. So I'm actually going to have two integrals here. So let's look at the first integral from 0 to a half. So how do I integrate 0 to a half here? Well, since it's undefined at a half, I actually go from 0 to c and then take the limit as c approaches 1/2 from the left. So then again you can integrate this using the power rule, and I got 3/2 times the cube root of 2x minus 1. And then if you let c approach 1/2 from the, well, I'm sorry, we're not ready for the c yet. So we evaluate this at c, and we get 3/2 times the cube root of 2c minus 1. And then if we evaluate it at 0, we get 3/2 times the cube root of 0 minus 1. Okay, well, now let's let c go to a half. If I let c go to a half, then this is going to be 2 times a half, which is 1, and 1 minus 1 is 0. So this term right here is going to become 0, and then this term is minus 3/2 times the cube root of negative 1. So I'm actually going to get 0 plus 3/2. Okay? Now, then the other one, if I do the other integral from 1/2 to 2, integrate from 1/2 to 2, I would actually integrate, since it's undefined at 1/2, I would integrate from c to 2, and then take the limit after I integrate as c approaches 1/2 from the right. So, I get the same function when I integrate, but now I'm going to evaluate it at 2. So I evaluate this at 2, and I get 3/2 times the cube root of 3, and then minus 3/2, and then let c go to 1/2, and this is going to go to 0. So I actually get 3/2 times the cube root of 3 minus 0. And then we have to add those two together. So this integral converges to the sum of those two functions. Okay? Okay, here's some practice problems if you want to freeze the video and look at these problems down here. And you can give those a shot. And let me show you, let's see. Did I have a practice problem on these others? I may not have had a practice problem on those. Maybe I put them all together. So maybe that's what I did here. So let's get down there. Yeah, I put them all together because this one goes from negative infinity to infinity. So that's a type 1. And so anyway, you can look at those and give those a shot. Now I'm going to go ahead and show you something else that you might find interesting. There's a couple of tests for convergence that you can do with integrals. And when you talk about sequences and series, you'll see a lot of tests for convergences of sequences and series. But really here, basically this just says if f of x is less than or equal to g of x, this says that the integral from a to infinity f of x converges if the integral of g of x converges, and then the integral g of x diverges if the integral of f of x diverges. And here's why. If g of x converges and f of x is less than or equal to g of x, then it's got to be smaller than g of x, so f of x would have to converge. But if f of x were to diverge and g of x is greater than or equal to f of x, then g of x must diverge. So that's a basically is what that's saying. So here you have sine squared of x over x squared, and you can actually show that since the value of sine has to be between -1 and 1, so if you square sine, then it's got to be between 0 and 1. So you could say sine squared of x over x squared is always less than or equal to 1 over x squared on the interval from 1 to infinity. And so you can easily show that this, I'm not sure if we showed this or not, we may have, but you can show that this integral converges, and since this integral converges and this function is less than or equal to that integral, then this function must converge. And then on this next one, you can actually show that this function is actually greater than or equal to 1 over x. And if you tried to integrate 1 over x from 1 to infinity, you would find that it diverges. And since it diverges, then this integral from 1 to infinity must also diverge. And I've got one more little tidbit for you to share with you. There's another test called the limit comparison test, and if the limit of the ratio of f of x over g of x as x goes to infinity is some real number between 0 and infinity, then either both of these functions converge or both diverge. Okay, so that's called the limit comparison test. And so one way to do that is we could compare it with the 1 over x squared. We know 1 over x squared converges. So let's take the limit of this function over this function and see what we get. So if you take the limit of 1 over 1 plus x squared over 1 over x squared, you get x squared over 1 plus x squared as x approaches infinity, and you can easily show that that limit is 1. And so since that limit is 1 and this function converges, then both functions must converge. Okay, now they do converge to different values. One converges to 1, one converges to pi over 4. And then the last one here, I have 1 over e to the x plus 3, and if I compare it with 1 over e to the x, well, 1 over e to the x plus 3 over 1 over e to the x is just e to the x over e to the x plus 3 as x goes to infinity. And as x goes to infinity, this becomes infinity over infinity, which is an indeterminate form. And L'Hopital's rule, using L'Hopital's rule, I can just take the derivative of the top and bottom, and I get e to the x over e to the x, which is just 1. And we know the limit of 1 as x approaches infinity is just 1. So again, since this function converges and we got to limit a positive finite value, then this limit that we compared it with must also converge. Okay, so that's pretty much it on these improper integrals, and I believe that's all I have for these problems on integration techniques.